Okay, so let's do this moment of inertia of a sphere again, but we're going to do it in a fun way because it's all about fun. So just a recap of what I've done so far. So I want to find the moment of inertia of a sphere as it rotates about an axis through its center. The moment of inertia is defined as the sum of the mass pieces times the distance from the axis of rotation squared. And so in the past video, I did this by finding the moment of inertia of a ring, which is pretty easy, and then finding the moment of inertia of a disk by breaking it into a bunch of rings, and then finding the moment of inertia of a sphere by looking at it from the side and then breaking this into a bunch of disks. And so the moment of inertia, I guess I should finish that. The moment of inertia of a ring, mr squared. The disk is 1/2 mr squared, and the sphere is 2/5 mr squared. And I did that by using calculus to integrate. And I had a great time. I don't know about you. But I'm thinking, wouldn't it be cool to do it in Python, to break this into individual masses, a whole bunch of tiny little masses, and then each one of these masses I could find m and r squared, and then just add up the discrete moment of inertia and compare that to this. So that's what I'm going to do. And the question is, well, how do you build all these masses in Python? It's not super trivial, but I'm going to use the same method. So the first thing I'm going to do is build a ring. So I'm going to take this, and the first thing I'm going to do is pick my size of my piece. And I'm going to use spheres of length ds. Okay, so that's my element size. I've drawn it big. And then what I want to do is, take that and just break this ring into a bunch of pieces and go all the way around. And so once I build that, if I can build that, what I'm going to do is get the positions of all these, the vector positions, right? And this will be a ring of size r, let's call it r for the radius of the ring. That's all I really need. I need the location of the ring, but that's not super important. I need the radius of the ring. Okay, so I'm going to have a function that builds the ring of pieces. Okay, and then it's going to export all the positions of the pieces. Now, the one thing that I did have trouble with was, how do I break this in? Because imagine I have a small ring, and a big ring. I want the big ring to have a bigger mass than the small ring. I don't want them to be the same masses, so I want this one to have fewer pieces in there. So if I look at the circumference around here, that's going to be, circumference is 2 pi r. And then I want to divide this into pieces, right? So how many pieces would this be broken into? I did this twice. Let's see, n is going to be equal to, if I break this into ds steps, then the number of pieces is going to be 2 pi r divided by ds. Okay, that's fine. That'll tell me how many pieces are in that ring. Now, I'm thinking this through. I haven't planned this stuff because I didn't really want to plan this too well. Now, what do I do? So if I have n pieces, I guess I could break this into d thetas, right? So as I start to move to the next one, I'm going to have a d theta shift, where d theta is going to be 2 pi over n. Yeah, that'll work. And then I guess I could say d theta is going to be equal to 2 pi divided by 2 pi r times ds. So this would be ds over r. Yeah, I think that works. So that tells me how much of a step size I have based on this preset size of a mass, right? And that will make sure that I have fewer pieces in my smaller ring than I do in my bigger ring, so that my bigger ring will have a bigger mass. Because you could imagine just building this graphically, but I don't want to have too many pieces close in because it wouldn't be a uniform mass distribution. And in fact, while I'm thinking about that, this would be a great place to find the moment of inertia of a non-uniform sphere. But I'm still in the ring. Okay, that would build my ring. And if I make a function that builds a ring of size radius r, I should be all set. Because then I can use that to make a function that builds a disk out of rings that are a thickness ds, right? and then I can use that to build a sphere out of disks. So I'm going to have three functions. I'm going to have a function that makes rings, a function that makes a disk from the rings, and a function that makes a sphere from the disks. And then at the end, I'll have a whole bunch of masses. I can just sum up m times the radius squared, and that'll be my moment of inertia. Now, and then so if I take m equals 1, r equals 1, which I'm going to use, then the moment of inertia should be 2/5. It won't be exactly that because I'm doing a discrete analysis. But I can always break it into more pieces by making my piece size smaller, and that's what I'm going to do. Okay, I think I'm kind of ready to build this. So let's jump over to Python and let's just see how far we can get. I'm going to wing it because I like to do that. You know, the Han Solo programming, I'm making this up as I go along. So let's do that. Okay, so I'm in Python. I'm in Trinket. You know I love Trinket. If you don't, I love Trinket. So I've already started the program without you. I'm sorry. I wrote down the radius of the sphere and the mass of the sphere. Not a big deal. Okay, let's see. I'm going to, I need to first pick the size of my piece. Let's just start with, if I have a radius of 1, let's start with a 0.1. That's the diameter of my little tiny piece size. Okay. So now what I'm going to do is like start at theta equals 0 and kind of work my array around. And once I know theta and the r, I can build these things. So let's just say theta equals 0, not 9, 0. Now I need to calculate d theta. Okay, so how big of a ring do I want? Let's just do r. Let's just do the whole size r. No, let's say r disk is, I'm gonna make it a little bit smaller, equals 0.3. I'm just picking stuff. So now I need my d theta. What's my angular step size? Like I just said, d theta is going to be equal to ds divided by rd. And that will tell me the number of the angular size for each of my steps. Now I'm just going to say while theta is less than 2 times pi, so that'd be all the way around, colon. So in Python, in case you can't remember, you put a colon at the beginning of the loop and everything that's indented is part of that loop. So the first thing I'm going to do is find the vector position of my mass. So I'm going to type this out, r equals vector, and I'll explain it. 0, I'm going to have my ring centered on the origin in the x-axis. So the axis will be the x-axis. 0, rd times cosine theta, rd times sine theta. So if you think about sine theta, cosine theta, I should have drawn a picture. So imagine a vector going straight up the z, let's see, the r axis. No, I'm going to be in the RZ direction. Yes, the y-axis. And the angle's measured from that. So r cosine theta is the component of that vector in the y direction. Rd sine theta is the component in the z direction. So then I can find out where that actual mass is. Now what I'm going to do is I'm going to put a sphere there. And I don't need to actually give it a name. I'm just going to say sphere. It's a built-in function in Python. The position is going to be r, which I've already said. The radius is going to be, so this ds is the size of the piece. So the radius is going to be half that, ds divided by 2. I'm going to turn on, let's put color equals color dot red. And let's do this, let's just leave it like that for now. Okay, now I need to increase my step size, my theta. I use my theta to increase this. Theta equals theta plus d theta. And I think that should work. Let's save this and run it. It worked. Look at that. I want this to be, since these are going to be, I want it to be partially transparent. So let's see, opacity equals 0.6. So it's kind of translucent. Yeah, I like that better. Okay, and then I could change this to make it a little bit bigger. Let's just see if I make this really, you do notice a problem up here. Notice that I get a little bit of overlapping over here. I think that's not too much of a problem. It's going to be more noticeable as this gets smaller. If I have a smaller radius, I should have, the most important thing is I should have smaller number of pieces. And I didn't count. Yeah, okay, that's good. That's going to help. But there you can see there's definitely an overlap there. I think that's going to be okay in the long run. Let's just not worry about it, and let's just see what happens. If it's bad, it's bad, and that's fine. Now, the other thing is I'm going to need a list of the values of these things. So let's go up here and say M S. Why is that S? Of masses of the sphere is equal to a list. And then down here, I can say ms equals ms plus r. So what that does is that adds the vector r to that list. Now down here I can print out, just to show you, ms. It sure is slow. Okay, so there's the list of all my positions of my masses, and I need that to find the moment of inertia. But I'm just going to build up a list of all the masses, and then I can find the moment of inertia later. Okay, so let's turn this into a function instead. Okay, so let's go up here. And I'm going to do some bad things. Okay, I'm going to say def ring. I need the x location of my ring because I need to be able to move those rings at different places. Yeah, and then I need the radius of my ring. And I'm going to use my step size up here. So I'm going to have that as a global variable, and I don't declare it as a global because I'm super lazy, and I just don't like that. So I do need theta. Let's put that in my thing. RD. No, that's going to be, let's call this RD. Wait, XR. Why am I calling RR for ring? Ring. D theta, that's fine. Okay, MS. Now this one I'm going to have to say MS. Let's say MR for the mass of the masses in the ring. Yeah. And then I indent this, indent that. And then, oh, there it did use RD. What's weird, it worked. Oh, I did do R. Let's change that to RR. That's right. RR, the pirate way. Get it? RR. Now I'm going to make the sphere. That one's fine. Then I'm going to increase theta. This is going to be MR, MR, and that's that. Now what I'm going to return, right? In a function we need to return something. So I'm going to return. That needs to be indented. Return MR. So let's just say, watch this. Print ring the x location. Let's move a different x location. Let's say negative 0.1 and a radius of 0.7. And this should print out the list of all the masses because it's returning a list of things. I have a feeling it's not going to work. I should save it, don't I? Shouldn't I? Okay, let's run it now. And it's going to be slow. DSRD. Aha. RSRR. See, when you change names, you're always going to make a mistake. That's not 0.7. 0.7. R. Oh, here. That's the problem right there. Okay, look at that. See, and you'll notice the bigger rings, you're not going to get as much overlap because you're going to have a better chance of fitting an integer number of spheres in there. I'm pretty happy. I'm pretty happy. Okay, now we can build a disk. Okay, so we're going to use a disk. We need XD, the X location of the disk, and RD, the radius of the disk. So the first thing I'm going to do is, now I'm going to reuse the variable r. Forgive me. Actually, let's say RD temp. That's stupid. Is equal to 0. Because what I'm going to do is make a ring of radius RD temp and then increase that until I get to where I want to be. I'm also going to need to make my list of masses. So MD is a list. It's empty. Now I'm going to say while RD temp is less than RD. That's the disk. Yeah. Then do the following. I'm going to just add in MD equals MD plus. So up here, did I say about this word? So this is adding I did say that, adding a value to the list, because MR is a list, and then I add the value R in there. So I'm going to do the same thing down here, except here my list item is going to be a list. So I don't need to do this. I can say ring, and then on XD R temp, RD temp. Yeah. So this is ring, not rind. Rind. That's rind. So this is going to return it's going to, one, build the thing and show it. And number two, it's going to return a list of all the positions in that ring and add it to the total disk. And then I need to increase the size of the radius RD temp equals RD temp plus DS. And then I need to return MD. Is this going to work? I think it's going to work. Oh, I didn't make a sphere. What's the wait? MD equals ring XD R temp. Maybe it didn't run. What the heck? Oh, I never called it, dummy. Okay, so I need to make a ring. So let's say disk of at x equals negative 0.1, radius of 0.7. I'm so silly sometimes. Okay. Check that out. In there you can see that overlap problem right there, but again, I'm not really worried about it. I could print that out, but I trust that that's working. Okay, now we need to build a sphere. So let's say def sphere, and it's going to have I guess it has a location of the center, but I really just need the radius. So let's just say RS for radius of the sphere. That's all I'm going to enter into it. And then I'm going to say, I'm going to start with my x value of x equals RS, right? Because I'm going to, negative RS. So I'm going to start in the negative x-axis. And then I'm going to, I need to calculate, I should have included this. What's the radius of that sphere at that location? So let me just write down here, x squared plus y squared equals r squared. That's the equation of a circle that covers the sphere. And I know my x value. And the y is going to be equal to my actual sphere. Right. So let's just say y equals the square root of rs squared minus x squared. So this first one's going to be 0. And I think that's okay. But let's just see what happens. And that's actually the radius of my circle. So now I'm going to make a disk. So I'm going to say disk. And the x location is going to be equal to x. And the radius is going to be equal to y. And I need to make a list. ms for the sphere equals blank. So I should say this. ms equals ms plus disk. I'm getting kind of scared, to tell you the truth. I just feel like something's going to break. Now I need to increase my value of x. So x equals x plus ds. No, I never did a loop. Okay, so I'm got this all screwed up. Let's move this over there. And put that back. If this works, I'm going to be like pumped up. Okay, while x is less than rs, do the following. Calculate y. Use that to make a disk. And then increase x. Is it that easy? Okay, let's say. The one thing I didn't do, which I can do down here, let's just do this. So let's say sphere 1. Is this going to work? Okay, I'm running it. Something happened. Cannot read property of u in line 30. RS negative u. What? Def sphere. Oh, that's why. I can't use the function sphere because it's already built in. So let's just call it sphere. Sphere. How about that? Okay, now I'm going to run it. Weird. That's not right. Def sphere. Aha, that's fine. Because this is... okay, that's right. I got to change that name too. Okay. That's a disk. So it didn't make... It made a disk. So it said sphere XR MS while X is less than RS. And Y equals that. MS equals disk. Oh, RX is right. That's X right there. Y. Why did it only make one? Arg. I feel like stopping and really just figuring this out. Because I feel like I'm a little lost. You know what I'm saying? Okay, but there's got to be something. So while X, it feels like it just does it once. So X is negative RS. So I should do this as not a function, maybe. Let's just do this. That way I can like play around with it more. Okay, so let's say X equals negative R. And then I'm going to say MS equals nothing. And then I'm going to say while X is less than R, do the following. Calculate Y. Y equals the square root of RS. Ooh, RS. Yeah, that's right. R squared minus X squared. And then just do these disk. Let's just do disk. I'm not going to worry about the numbers. X, Y. And then X equals X plus dx. And let's just print out X. That's so we can see if it's changing. Dx. Oh, I want ds. Okay, so it did increase. It started off with X of -1. Okay, great. It increased. That's a weird number right there. So it is increasing X, but it's not moving the disk. So the disk is x. Let's just try this. Let's try disk of, let's say, 0.3, 0.3. It should make a disk at x equals 0.3 with a radius of 0.3. And it did not. Okay, I'm going to stop. I'm going to figure this out. I'm going to come back to you. Okay, I figured it out. It was a dumb mistake. You know it's going to be a dumb mistake. So what I did was in my ring, that's fine. No, it's not fine. Right here, I had this at 0. Remember when I first built the ring, I said it's going to be centered at the origin, and I had this parameter xr for the center of the ring, but I never used that. So it was building spheres on top, disks on top of each other. So I went ahead and I built a function. I'm not finished yet, but I built a sphere. It's not a sphere, it's a sphere function. And so it's it only need one parameter now, the radius. I'm going to have it centered at the origin. Here's my list of masses. Start off with x is negative r. It's all the same thing I had before. And then I'm going to add up while x is less than rs. I calculate the y, and then blah, blah, blah. Okay, so I put it really low. Let's go back to this. It looked really kind of weird. Point with a ds of 0.1. I'm going to run it. My computer starts getting loud because I think I'm asking it to do quite a bit. Okay, and you see there, it's like, what? That's not a sphere. And I think it is, right? It's just that you can only fit so many so many of these pieces in here in order to get to the next level. You know, it just doesn't fit in there. So that's fine, right? It's not it's a Lego sphere, right? It's a sphere. Okay, I'm going to I'm going to show you. Let's make this half as big. And it's going to take longer to run. Then I'm going to switch back to the other way just so I can finish up my calculations. It does take longer. And I don't really know why it takes so long. I mean, I guess there's a lot of pieces in there. Should I tell you a story while we're waiting? Because, I mean, apparently this is going to take forever. And it's moments like this you're thinking, did I mess up? Is this just taking a long time to run, or did I make a mistake? I think it's just taking a long time to run, because all I did was change the step size, right? No big deal there. Oh. Yeah. Okay. Again, you can see this little flatness up there, but it looks a lot better. It looks spherical. It doesn't like to rotate very fast. There we go. It's rotating. I'm not going to go anything smaller than this. I'll give you the link. It is cool though. Did you not think that's cool? Okay, let's make it back to 0.1 and run it just so it's not sitting there with all those masses on there. And now I need to calculate the moment of inertia. So the first thing I need to do is to find out how many pieces. I need to know the mass of each piece. If the total mass is 1, then the mass of each piece is the mass divided by the total number of pieces. So let's go down here, down to the end. Let's see, and sphere 1. Let's say total mass equals sphere 1. So that's a list of all my stuff, right? That's all the things I have in there. Now, the first, I want to know how many pieces I have. So n is going to be the mass. No, it's just going to be the length of that list, the length of total mass. Let's just print that out. Number of pieces. In. Okay, I'm going to keep going. Now I'm going to say dm is going to be equal to m divided by n, right? The total mass divided by the total number of pieces. Now I can go through and calculate I. So I is a sum. We're going to use the summation. So I is equal to 0. I'm going to start off at 0, and then I'm going to say, can I do this for I in total mass? So this will go through each element in total mass, and I is a vector here. So, I'm going to say The moment of inertia I is equal to, now, I need to take the mass of each piece, which is dm, times its radius squared. Now, its radius squared is not the radius squared. It's the xz coordinate squared. So it's going to be equal to dm times I dot y squared plus I dot z squared. Okay, so is that right? That's r squared. Yeah. Plus I. Right, so I'm adding it to the other thing. And I think that's it. Okay, now print moment of inertia equals I. And then let's print theoretical I equals, it'd just be 2 divided by 5. Because it's 2 divided by 5 times, well, let's just go ahead and do it. 2 times m times r squared divided by 5. Is that going to be right? Let's do this. I don't know if it's doing the, I think that would be 2/5 squared. Okay. You ready? I will run it with more pieces. Len of undefined. Oh, I didn't return that. Okay. So I need to return ms. Come on. Okay. All right. 4,000 pieces. 0.39 is the theoretical moment of inertia. The theoretical is 0.4, so that's pretty good. Okay, I'm going to run it at a smaller value. I guess I'm going to have to do half as much, would be 0.05, and you know how long this is going to take, but I'm doing it. I'm going to save it, and I'm going to be done after this run. So what can I tell you while it's running? Why would you do this? Why would you care? I care because, one, it's fun. It's like Peter Parker in Spider-Man Homecoming. You know you can't record. Why are you recording this? And he's like, well, you know, it's for fun. And this is just for fun, right? I think it is fun. It helps us practice with lists and loops and functions and numerical integration. It's just a cool thing. Once you do this, it's possible to use this same process for things you couldn't integrate. Most of the moments of inertia you can integrate. It's not too terribly difficult. But, you know, imagine there's some function that you don't even know have a value for the density. You have data for it. Okay, that's pretty good. Look how many pieces I have, though. That's a lot of spheres. And you could do this without drawing the spheres. It'd run way faster, but I wanted to draw it, right? Because it's not just physics, it's art. Okay, so there you go. I'll link the code down below. I'll link to the other versions of this, and you guys can have a fun time with it. I'll talk to you later.